All right, guys, so today we're going to look into the inverse of a function. So this will touch on a little bit of information that we learned about in Unit 1, because we talked about what is a function, what does it do, and then we're also going to combine some of our transformations knowledge once we get to the graphing part of this. So in Unit 1, we really talked about functions. When we introduced the idea of a function, it's kind of like a machine. It takes something in, it performs a set of operations, and then it spits something out. Okay, so we talked about like a couple things in real life that do this. A toaster, we put bread in, it toasts it, we get out toast. So there's lots of different machines that we know of. In this case, our operations, I'm just going to wait till everyone's ready here. Okay, so in this case, our operations are multiplication, division, addition, subtraction, squaring, square rooting. Gentlemen, do I need to separate everybody here? What's the problem? Okay. So an inverse function. An inverse function is going to basically undo what the original function does. That's its operation, or that's its purpose. So in other words, it's going to do the opposite operations of the original function in the opposite order. Okay, so there's a notation that we use for the inverse of a function. So if I start with the function f at x, its inverse will use the notation. It looks kind of like an exponent of -1. It's not an exponent. Basically what this reads as is f inverse of x. Okay, this is not equal to, or I should say this is not an exponent of -1. This is just a notation meaning inverse. Okay, so please do not treat this like an exponent of -1. It doesn't need to be isolated for. It's basically just indicating that it's the opposite function of f at x. Okay, so we have the function f at x equals 2x plus 3. Using the information here, so the goal of the inverse function is to do the opposite operations of the original function in the opposite order. So we're going to see if we can create the inverse equation for 2x plus 3. So what might be good is if we figure out what the order is in which we do things here. And what each operation is. So what do we do first in this equation when we enter in an x value? Zach? Pardon?
So like find A, K, B, C.
We're not really talking about transformations here. I'm just talking about like what comes first. Multiply, divide, add, subtract, and
Multiplication, division first, and then adding, subtracting.
okay, so in this equation here, what operation happens to x first? Charlie? We multiply by 2 first, right? That's bedmass.
X times 2.
Does that make sense? So the first thing I do when I put an x in here is I multiply it by 2. And then the second thing I do is I add 3, right? Okay, so that's what f at x does. So can somebody tell me what f inverse of x does? And in what order it does it? So opposite operation in the opposite order. Martez?
Take away 3.
Take away 3 first,
That was divide by 10.
and then we will divide by 2. So opposite operation in the opposite order. Can someone create an equation from this information? So our function takes an x, it subtracts 3, and it divides 2.
Is it
Thomas?
x minus 3 over 2?
Yeah. X minus 3 all over 2. Perfect. So we can actually do a little check to make sure that our inverse is doing the opposite of our original function by choosing an x value to plug into f at x and seeing what we get out, and then plugging what we get out into the inverse function and seeing if we get back the x value we chose. So Emma, can you choose me any x value?
4.
X value of 4. Okay, so choose an x value. We choose 4, so we're going to evaluate f at 4. That means we'll take 4, we'll multiply it by 2, and we'll add 3. So we're going to get 11. So if I've done this correctly, I'll answer your question in one sec, Thomas. If I've done this correctly, if I enter in that output into my inverse function, it should spit back out what I started with in the original function, which is 4. So if I evaluate f inverse at 11, I'm going to plug it into this function here. It will be 11 minus 3 over 2. If it spits out 4, I've done it correctly. Okay? So they're basically opposites of one another, right? So if I sub in 11, it should undo all the operations that I just did to it, and it should give me back out 4. So here we get 8 over 2, and then we get 4. So because I got back out 4, we did the inverse function correctly. Thomas, you had a question?
It's following the rules of bedmass, right?
Yes. Does this make sense? Okay, so basically what we're saying in this kind of original part here is that the regular function f at x has a point 4, 11, and we're also saying that the inverse function has a point 11, 4. So the x's and y's of the original function and of the inverse function are kind of like swapped versions of one another. And we're going to use this idea to develop an algebraic method for finding this equation, because the more complex our f at x equation gets, the more complex our inverse function is going to be to find, right? So if we have a couple steps that can kind of lead us through that process, it's going to be a little bit easier for more complex functions. So here are your steps for algebraically finding an inverse. If you're dealing with function notation like f at x, g at x, whatever, you're going to replace that with y. You're going to replace that with y. Once you've done that, switch all x's and y's. So wherever you see an x, replace it with y. Wherever you see a y, replace it with x. And then your job is to isolate for y. And what this does is in the isolation process, as we're moving things, it undoes bedmass, right? So it undoes all of the operations of the original function. And then once you have y isolated, you're going to put this back into function notation with the little inverse notation. Okay, so let's try it. So I'm going to show you how we would have done the equation above, just using the steps. So first step is to replace f at x with y, or whatever function notation you have. Second step, we're going to swap all x's and y's. Third step, get y by itself again. So if you know grade 9 math, you can do this, okay? So I believe in all of you.
I don't know.
So we're going to isolate for y. We're going to bring the 3 over to start. Becomes negative 3. And then we will divide out 2. Okay, so this is what we get. Okay, and then the last step here, we're going to replace our y with function notation. So whatever the name is of your function, you're going to replace that with inverse notation. Okay, and this is actually the function that we got above, and we use the algebraic method to find it. Now, if the function is like a little bit on the easier side, and you feel confident that you can create the inverse equation like we just did above, rather than doing this whole algebraic method, I don't need to see the algebraic method. If you can show me some reasoning, like I showed this reasoning here, and this reasoning here, and then I created the equation, I'm totally fine with that if you feel confident. If you want to do the algebraic method, that's fine. If the function is more complex, I would encourage you to use the algebraic method anyways, because it's going to get a little bit more confusing if you're just kind of trying to figure it out in your head. Okay, so let's try a few here. So first step, replace your function notation with y. Okay, so that's step number 1. Step number 2, swap x's and y's. So wherever you see an x, replace it with y. Wherever you see a y, replace it with x. And now we want to get y by itself again. So let's multiply up the 4. Those will cancel. And we'll divide out the 3. So we'll get 4x over 3. That's the third step. And last step, we're going to replace the y with its inverse notation for g at x. So g inverse at x, or g inverse of x, equals 4x over 3. Okay, I think this one's a bit of an easier one in the sense that if we look at the original function, the operation is that we take x, we multiply it by 3, and we divide 4. So the inverse function is going to first multiply by 4 and then divide by 3. So opposite operations in the opposite order. If you can figure that out without having to do all of these steps, that's fine as well. Just make sure you show like a little bit of reasoning at least as to how you got that answer. Okay, I think we can figure out this one without having to do the whole steps, right? What does this function do first?
Multiplies.
It multiplies by 4,
And then adds by 3.
and then it adds 3. So what does the inverse function does? This is what, or h at x, I guess it's called. So what does h inverse do? So at first, it first will subtract 3. Right, and then it will divide by 4. So who can create our equation for us? George?
It would be the inverse of h.
Mm-hmm.
X equals x minus 3 over 4.
Beautiful. Okay. So either one of these ways are fine. If you feel more comfortable, and more certain doing all the steps, you can definitely do that. But for easier ones that have like 2 operations, you could probably figure it out. Charlie? I won't ask you to do any specific way. I just want to see evidence of your thought process. So either like show me this or show me your steps here. Any questions so far? We're okay? Okay, let's try another one. I'm going to go through the process here, the steps. So replace with y, swap x's and y's, and now we want to get y by itself. So I'm going to move the 1 over. I'll get x plus 1, and we have y squared. Okay, this is one little important thing when you are solving and you have a y squared. When you go to undo that squared, we know that the square root is the opposite of squaring something. In a solving process like this, you need to do plus minus in front of that root. Okay? When we think about something like x squared equals 16, you don't have to write this. There's actually 2 answers to this when I solve it. And that's because when I do the square root, I'm actually considering both possibilities that could have got me to 16. -4 and +4 squared are both 16. So that's kind of the idea behind this. So make sure you put plus minus there. These ones will cancel. And we have y equals plus minus x plus 1. And x plus 1 is all over this, all underneath the square root. Okay, so that's our third step. Last step, we just replace with inverse notation. Okay, for this next one, the root is just over the x part, not over the 2. Okay, so step by step, replace function notation with y, swap the x's and y's, and then we want to get y by itself again. So the first thing that I'm going to do is bring over the positive 2, becomes x minus 2. And how do we get rid of a square root?
Square both.
Square both sides. So square this, these will cancel. And we will have y equals x minus 2 all squared.
So if I switched it into x plus 4,
Nope. That is a math crime right there.
why is that math? Or x squared?
X minus 2 squared is x minus 2 times x minus 2, and then you FOIL it, right? You can't distribute a squared just into each term like that. Okay, last step. We replace y with the function notation, our inverse. Okay, any questions so far? Can I clarify anything? We're okay? What did you say, Zach? You okay there?
There's a heart on my graph. Yeah,
Oh.
there's a heart number.
Okay, let's try a couple more here. So we'll go through the steps. Replace with y. Swap x's and y's. And then your job is to get y by itself. What should we do first here to get y by itself? We need to get rid of this division by 5 first. You cannot touch anything in the numerator until you've done that. So Thomas, what should we do?
Multiply by 5.
We're going to multiply each side by 5. Those will cancel. Next, we're going to move the plus 3 to the other side. Becomes minus 3. And then we'll divide out the 4. So it's this whole thing divided by 4. Okay, and then last step, use your function notation. We started with h at x, so this will be h inverse of x. Okay, most of this is grade 9, right? So hopefully this isn't like, well, most of this is just isolating, right? Like isolate for a variable, or like isolate for a variable. So we did all this BEDMAS and isolating stuff in grade 9. The only extra grade 11 part is these first 2 steps, and then the last step. But the bulk of the math that you have to do here is just grade 9 algebra work. All right, so the root here is just going to go over the -½ and the x. So let's just go through our process here. Replace g at x with y. Swap x's and y's. And then we're going to start to isolate for y. What's the first thing that I do here to isolate for y? Yes, we need to move the 3 first. It's going to become -3. Okay, then we're going to divide out this -2. You can't touch anything under the square root until you've moved the things on the outsides. So do your -2, these will cancel. And I also can't touch anything in here now until I've removed the square root. So how do we get rid of that square root? We're going to square. Okay, fastest way that you can get rid of a fraction from one side is multiply by its reciprocal. So what's the reciprocal of negative 1 over 2? Negative 2 over 1, yes. So, or negative 2. So if I take both sides and I multiply by the reciprocal, negative 2 over 1, or in other words, just negative 2, we don't have to put the over 1 part, then the 2's will cancel, and the negatives will cancel, and y is left by itself. So the easiest way you can eliminate a fraction, a multiple of a fraction, multiply by its reciprocal. Now we have y by itself. I'm also just going to clean up a little bit what's inside the bracket, and I'm going to apply the squared onto the x minus 3 in top here, and also to the negative 2 on the bottom. So what's negative 2 squared? It's 4. So I have over 4 here. And I'm just going to kind of like gather this, because this is kind of like an a value right here, if we're thinking about transformations. So it's like negative 2 over 4, which can actually be reduced to negative 1 over 2. Okay, so just kind of like thinking about this as if it's over 1, and I'm just bringing this 4 over. Okay, and I'm just going to replace y with its function notation as well, which is g inverse at x.
Can you common factor the top and the bottom?
Common factor the top and the bottom.
Like just make it negative 2 on the bottom.
Like here?
No, like at the top where it's negative 2.
Yeah.
And then the 4 on the bottom. That would be the same thing as
Like
negative
this,
2
right?
on the outside. So then couldn't you just make it negative 4 on the bottom and then not have that like fraction? You know what I mean?
I'm confused as to what you're asking me. So are we looking at this step?
No.
Yeah.
Okay. And what are you
So
saying?
Let's say if you were to bring that together.
Yeah.
Negative 2 and then the brackets x minus 3 squared over 4.
Oh, wait.
Yeah, sure.
So then can't you just take the negative 2 and the 4 and then make it x minus 3 squared over negative 2?
Yes, but if we want to properly see like the transformation, then we would write it like this. So I would say this is your better bet, because if I then ask you to graph the inverse function, then you can actually see what the a value is. But yes, technically you could express it in that way as well. Okay, this is a little challenge question. We're not going to do this one, but if you're interested in trying it out after the lesson, you can try it and I'll let you know if you're right. Okay? It's a little extension question.
Will that be on our test?
No. Okay, so that was algebraically. That's how we look at an equation and we algebraically figure out what its inverse equation is. Let's take a look at what happens when we graph. So we have the line y equals x, and inverse functions are actually reflected if we take our graph and we pretend to kind of like fold it over the line y equals x. Inverse functions will essentially kind of like take these and reflect them over on the other side as if it's like mirrored. So the easiest way to figure this guy out is inverse functions essentially have points that are swapped versions of one another. That's what we looked at above in the very first example when we did our check. So our little circle, what are the coordinate points of our circle? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 8. And then the heart?
-3.
Okay. -3, +4. Yep. And star?
-5 and 1.
Okay, so this is our regular function. Maybe we can call this the function f at x. So if these are the points, then f inverse of x is basically going to have the same things. Okay, so we'll get similar points, except for the x's and y's are going to be swapped versions of one another. So we're going to have 8, 1 as our first one. So let's plot that. 1, 2, 3, 4, 5, 6, 7, 8, 1. It's going to be here. Oh, yes. Should be here. Nope, we don't switch the signs. It's 8 and 1. Do you guys also like that I did the inverse of the colors as well? Right. New heart for the inverse function becomes 4, -3. So you take the x's and y's and swap their locations. So 1, 2, 3, 4, 1, 2, 3. So we have a heart here. And then star, yeah, is at 1, -5. So 1, 1, 2, 3, 4, 5. Star is going to be here. Okay, so if we kind of look at this, you're going to kind of imagine over this line, if we fold our points here, the shapes are kind of flipped on the opposite side of this line, right? So does that look somewhat symmetrical if we tilt our heads a little bit there? Yeah. So that's basically what happens when we do an inverse function. So you guys can literally do, if we're doing a graphing question, come on.
Come on.
If we're doing an inverse function, you're literally going to do exactly what you already know how to do with transformations, and then once you're done your transformations on the original function, all you have to do is swap your x's and y's, and you can graph the inverse function, okay? So the only extra piece here is if I'm graphing an inverse function, I do everything as I usually do, and then I just swap the x's and y's to get the points of the inverse. Okay, so let's try it out. We're going to sketch the inverse of x squared. So this is actually one of our parent functions. So we can just use the key points of our parent function. Okay, so we're going to plot them here, just so you guys can kind of see visibly what's happening. We can also just sneak in there -3, 9 and +3, 9 as well, just because they can fit on our graph here. Okay, so here is f at x. And the inverse function, I don't even have to do like any calculations or anything. We're just going to take them and swap. So f inverse of x, x's become y's, y's become x's, just like what we do when we do the algebraic method here. Okay, so swap your coordinates, and then we're going to graph each of these coordinates here. So okay, and then we'll label this f inverse of x. Okay, so if you kind of imagine, tilt your head to the side a little bit and imagine that kind of getting folded over that line, it should look somewhat symmetrical. Can I scroll from this? Thomas, question?
To get rid of an exponent, do you square root?
Depends what the exponent is. If the exponent is a squared, then you square root. If it's cubed, then you cube root. If it's 4, then you fourth root, and so on. Yeah. Also, guys, I just want you to notice, what's the opposite of squaring something? square rooting something. But we did talk about if I'm undoing a squared, what do I have to do to the square root? I have to do plus minus. So the inverse function is actually plus minus the square root of x. What do you guys notice about just the upper half of this? What does that look like? It's the square root function. And because we do plus minus, we also get that bottom part as well. So those functions are basically like inverses of one another. But when you have the plus minus there, you get this bottom piece. So this upper piece right here, this is the square root of x function.
Cool, baby.
Yeah.
Did you realize that now?
Oh, that's crazy. Wow.
All right, let's try one more here. Okay, so guys, every single time I have a test on this unit, okay, this is going to be another one of those things where I tell you don't be that guy. Every single time I have a test for this unit and I say graph g at x and graph g inverse of x, people take the time to do transformations and graph this function, and then they go algebraically and try to find the function for g inverse of x, and then take a bunch of time to graph transformations of that function. We don't have to do that. All we need to do is figure out the points for this function, and then when I go to graph g inverse of x, I just swap them. Okay? So we're not going to be that guy that does a bunch of extra work that he doesn't need to do, or she doesn't need to do, right? We're not going to be that person. Okay? No, I always just say that guy. So what is the parent function here? What's the parent function? What's the most basic function? Square root of x. Okay, so let's start with the key points of the parent function. They are 0, 1, 4, 9, 0, 1, 2, 3. And then we're going to graph g at x. So to graph g at x, we need to set up our equations. We need to identify a, k, d, c from this equation. Lauren?
Well, a is -2. So,
Yep.
so y would be -2y plus 3.
Very nice. Someone do our x side for us? Charlie, do you want to try it? So the k value is -1/2. What's the reciprocal?
-2.
Right, so just -2 x. Okay, so everybody take your x's. We're going to multiply them by -2.
Yeah, everybody do that.
Ooh. And then we're going to take each of our y's and plug them in here. So multiply them by -2, add 3. Okay, you guys could have changed the scale for this, but I graphed this line y equals x, which means that if this is 1, this also needs to be 1 because this is the point 1, 1. So we're not going to change our scale here. So we're just not going to graph this point. Okay, we're going to graph these 3 points. And we know when we do this function, we always remember where 0, 0 gets transformed to, because that's the start of the new function, okay? So we're going to graph these 3 points, and our scale is just going to be going by ones here. So 2, 4, 6, 8, 10, and same thing on the y's. Okay, so first function, 0, 3. That's the starting point for my function, so don't have an arrow off that end. It's off the opposite end. Then -2, 1, and -8, -1. So we're going to have something kind of like this. This is our function. We'll just label it g at x. Okay, so if you're that person, then what you're going to do is you're going to figure out what this is algebraically. You're going to figure out the parent function, and then you're going to do a bunch of transformations to that parent function when you could just do this and swap your x's and y's. So all I'm going to do is I'm going to take these points and swap their coordinates. Don't change the signs. You don't have to do anything except for swap. Yep. Okay? Literally 5 seconds, and then graph it another like 10 seconds, and you're done. Okay? So don't do a bunch of extra work if you don't need to. Okay? Let's graph these points. Okay, and then we're going to label this G inverse of x. Okay, and I'm also just taking note, this point is the starting point of the inverse function. It's the starting point. So 0, 3 if it's the starting point of the original function. 3, 0 will be the starting point of the inverse function, this point right here. Okay, so make sure your two functions have those starting points. There's no arrows on those ends. It's just arrows off the opposite ends. Okay, does this look accurate to us? If we tilt our head and we fold over that diagonal line, do these look like they match up? No? Okay. Okay, any questions on this one? Can I clarify anything? Not too bad. We already know how to do the graphing part. The only extra part is just switching the x's and y's. Okay?
Do we have any more parent graphs?
Nope. Just the 3.